Morning guys, today we're going to start our trig ratio or trig unit. We're going to start that by talking about trigonometric ratios. And that's just really your basic right triangle trig that you've been working with since Algebra 1, all through geometry, and very much in depth in Algebra 2. Now, when we talk about right triangle trig, we talk about how the sides of a right triangle relate back to one specific angle within that right triangle. We're going to call that angle in this case theta. Now, as we label the sides of that right triangle, we start by labeling the side opposite of the 90 degrees, the 90 degree angle, which means it doesn't touch the 90 degree angle, so that's the hypotenuse. Then we're going to label the side opposite, meaning not touching the theta, the angle that we specify. We're going to call it the opposite angle. And then the remaining side is going to be adjacent. And it's adjacent because it touches theta but is not the hypotenuse. And as we've put that together with those three sides, we can then relate those sides together, two of them at a time, and that's what the trig ratios do. They don't really do any math, they just specify a specific ratio, a relationship of two sides within that right triangle. Now, sine is the ratio of the opposite length to the hypotenuse as it relates back to theta. Cosine is the ratio of the adjacent leg to the hypotenuse as it relates back to theta. And tangent is the ratio of the opposite length to the adjacent, opposite to adjacent, as it relates back to theta. Now there's a number of mnemonics that people have come up with, ways to remember these trig ratios. The most common one that I'm assuming y'all have used is this SOHCAHTOA right here. So, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. TOA, tangent, is opposite over adjacent. So, there's that one. A lot of you will use some old horse came hopping through our alley. The one I actually learned when I was back in high school was I remembered sine, cosine, tangent in that order. And then Oscar had a heap of apples. So whatever mnemonic you want to use, it doesn't matter. We just need to make sure that when I see sine, I automatically know that's opposite over hypotenuse. I see cosine, that's adjacent over hypotenuse. I see tangent, that's opposite over adjacent. Can't have any questions, can't have any confusion on that. Because if you miss one of those up, everything else works off of those. Everything we're going to do throughout this entire trig unit works off those three basic definitions of sine, cosine, and tangent. So make sure you have those down. Now, the first manipulation we have of those is the reciprocal trig ratio. Reciprocal meaning multiplicative inverse, meaning we're going to flip these fractions, flip these ratios over. So when we talk about sine's reciprocal, the reciprocal of sine is actually cosecant. And why it's cosecant instead of cosine, that's another story for another day. These are actually cofunctions, sine and cosine, secant and cosecant, tangent and cotangent. So they fit together by a different definition. The reciprocal has nothing to do with it, but we'll talk about that later. All right, now you need to remember that the reciprocal of sine is cosecant. So reciprocal means flip the fraction. Opposite over hypotenuse for sine becomes hypotenuse over opposite for cosecant. The reciprocal of cosine is secant. So when we do the reciprocal of adjacent over hypotenuse, we end up getting hypotenuse over adjacent. Secant of theta is hypotenuse over adjacent. And then the reciprocal of tangent is cotangent. That's the one time that the reciprocal trig ratio and the cofunction identities actually match up. But again, we'll talk about cofunctions later. So tangent of theta was opposite over adjacent. So when I do reciprocal of opposite over adjacent, I get adjacent over opposite. So cotangent of theta is adjacent over opposite. Now typically people won't come up with a mnemonic. I guess technically we could say CHOSHACAO. So you could go cha-sha-cow, but that's not as fluid as SOHCAHTOA. So if you can remember this one, you can easily create this one, and you don't have to remember an entirely separate mnemonic. Those are the 6 trig ratios. Those are all the ways we can relate two sides of this right triangle, or any right triangle, back to each other at any time. Now let's go work a few examples where we create these where we create all these trig ratios. Okay guys, here we've got a few examples of a couple of triangles that we know the sides. Now let's create those trig ratios based on those sides. So first off, we've got this 3, 4, 5 triangle, very, very common right triangle. We've identified this angle on the bottom right as theta. Now if I want sine of theta, we remember sine is opposite over hypotenuse. So the leg opposite of theta is going to be 3, and the hypotenuse is going to be opposite of the 90 degrees, so it's going to be 5. So sine of theta is 3/5. I don't care what theta is at the moment. All I'm worried about is what is the ratio of the opposite length or opposite leg to the hypotenuse. Now by the reciprocal trig ratio, the reciprocal rules, we know cosecant is the reciprocal. Cosecant is sine flipped over. So I get cosecant by taking the reciprocal of 3/5. Now we can do the same thing for the other 4 trig ratios. Cosine is adjacent over hypotenuse. So the adjacent leg has a length of 4. The hypotenuse has a length of 5. Secant is the reciprocal of cosine. So I'm going to perform reciprocal on 4/5. I get 5/4. Tangent was opposite over adjacent. Opposite over adjacent. So the leg opposite has a length of 3. The adjacent leg has a 4. So tangent of theta is 3/4. Then cotangent is going to be the reciprocal, 3/4. So that's going to be 4/3. So there's the 6 trig ratios given this angle theta for this 3, 4, 5 right triangle. Now note, if theta had been this angle, these would all be different because now this would have been my opposite length and this would have been my adjacent length. So it does matter where theta is within that triangle. Theta is a specific angle that we're looking at, or the trig ratios are specific to each different angle, because the opposite and adjacent are going to move based on where that angle is. Now if we look at number 2 here, we've got this angle theta, and it doesn't even have to be theta. I could use any symbol here. I could say that this is angle X. I call it angle alpha, beta, delta, gamma, mu, nu, iota, kappa, lambda. It doesn't matter what I pick. I could make this angle happy face. It really makes no difference what I label that angle as long as I'm consistent and I always identifying sine of that angle, cosine of that angle, tangent of that angle, cotangent, secant, and cosecant of that angle. So I just have to be consistent with my markings, and it doesn't matter what I label that as. Now, if I'm going to do sine, we remember that sine was opposite over hypotenuse. Well, opposite of angle X, the leg has a length of 1, and then the hypotenuse was a length of 2. Well, when I go to cosine, cosine was adjacent length over the hypotenuse. Well, I don't know what the adjacent length is. So if I'm missing a length, as I am in this case, I need to find the third side of a right triangle. Well, how do we relate the 3 sides of a right triangle? By the Pythagorean theorem. A squared plus b squared equals c squared. So a and b are the legs, c is the hypotenuse. So we'll say a squared, we'll make that the adjacent side. So adjacent squared, we don't know, plus b, we'll make that the opposite side. So a squared plus b squared equals c squared. And then we just solve for a, solve for that adjacent side. So a squared equals, do it again, a squared plus 1 equals 4, move the 1, a squared equals 3. So take square root and a equals 3. The adjacent side, square root of 3, has a length equal to square root of 3. Now, remember, typically we do plus or minus whenever we add square root into an equation, but because you can't have a negative length, a has got to be positive. Now, we will talk later on about labeling sides of triangles as having negative lengths, but that negative more denotes the direction that that angle is pointing. But we'll get into that in a couple of lessons. So we should have the adjacent side is equal to square root of 3, which gets me into cosine adjacent over hypotenuse. So adjacent length was square root of 3, hypotenuse was 2. So square root of 3 over 2. And then the tangent was opposite over adjacent. So opposite was 1 over square root of 3. And we remember our rules for rationalizing a denominator. Top and bottom by that denominator. So that's going to give me square root of 3 over square root of 9. So that's 3. Then we go perform all of our reciprocals. The reciprocal of 1/2, the reciprocal of sine is going to be 2 over 1. So that's 2. The reciprocal of square root of 3 over 2 is going to be 2 over square root of 3. Again, we rationalize. Square root of 3, square root of 3 gives me 2 square root of 3 over, I can't read that, over square root of 9, which is 3. And then the reciprocal, let's go back to right before we rationalized. 1 over square root of 3, the reciprocal will be square root of 3 over 1. So just square root of 3. So we get sine of x equals 1/2, cosecant of x is equal to 2. Cosine of x is square root of 3 over 2. Secant of x is 2 square root of 3 over 3. Tangent of x is square root of 3 over 3. And cotangent of x is equal to square root of 3. Now, that's how you take three sides, or a right triangle where we have all three sides, and we can find all 6 trig ratios. The 3 basic trig ratios and then your reciprocal ratios. Now, something interesting, this triangle right here, this right triangle, we talked about how this was a special right triangle because all 3 sides are whole numbers. This is also a special right triangle. This is, anyone, do you know? This is your 30, 60, 90 special right triangle. So if we look at, we remember that the side opposite, or the angle opposite of the 1 was 30 degrees. The angle opposite of the square root of 3 was 60 degrees, and the hypotenuse was 2. So that was our special right triangle, that 30, 60, 90, where the ratio of the sides was 1 square root of 3 to 2. And we'll take a moment and we'll look at the special right triangle, the 30, 60, 90, and the 45, 45, 90. All right, now these special right triangles, the 30, 60, 90 right triangle and the 45, 45, 90 right triangle. We call them special right triangles because they're easy to remember. I guess we could come up with a lot of different special right triangles. But not only are they easy to remember, for a 30, 60, 90 being 1 square root of 3 and 2 in the order of opposite of 30, opposite of 60, opposite of 90. If you want to think of it as 30 degrees, 60 degrees, 90 degrees as 1 square root of 3 and 2 to remember your opposites. And 45, 45, 90 as 1 square root of 2. They're also very good triangles to know because we can build so many other angles off of them. If I know 30, 60, and 45, then I can get an angle 105 because 105 is just 60 degrees plus 45 degrees. Or I could get the angle 15 degrees. 15 degrees is 45 degrees minus 30 degrees. So there's a lot of other angles that we can build off of these 30, 60, and 45. So that's why we consider them special. They're easy to remember and they are so useful in building a lot of other angles. Now this is where we're going to do the basic evaluation. Say I'm not given a triangle like I was in those last set of examples. I just see sine of 30 degrees. You got to know sine of 30 degrees off the top of my head. Well, I don't expect y'all to memorize all these. I think it's a lot better to understand where they come from and recreate them. So if I want sine of 30 degrees, I know for sine I need 2 things. I need the length of the leg opposite of my angle, and I need to know the length of the hypotenuse of the right triangle that contains 30 degrees. So without seeing the triangle, I have to remember this triangle. Not going to be given this. I see sine of 30 degrees, I automatically need to remember this. So I've rebuilt this triangle, and I can say opposite of 30 degrees is a 1. The hypotenuse for that triangle is a 2, so sine of 30 degrees is equal to 1/2. Secant of 60 degrees, going through the same thought process. Remember your ratio first. Secant is the reciprocal of cosine. Cosine was adjacent over hypotenuse. So the reciprocal of adjacent over hypotenuse is hypotenuse over adjacent. Well, for 60 degrees, what's the hypotenuse of the 60-degree angle? 2. What's the side adjacent? 1. So we get secant of 60 degrees is 2. Tangent of 60 degrees. Tangent, we remember through SOHCAHTOA. TOA, tangent is opposite over adjacent. Opposite over adjacent, so I go to my 60 degrees. Opposite of 60 degrees is square root of 3. Adjacent to the 60 degrees was 1. So it's just square root of 3. So there's 30, 60, using a 30 degree or 60 degrees from the 30, 60, 90 triangle. Now let's say we had 45 degrees. Well, if I've got 45 degrees, then I've got to come over and I've got to remember my 45, 45, 90 triangle. My 1, 1 square root of 2. So through SOHCAHTOA, sine is opposite over hypotenuse. Opposite over hypotenuse. So opposite of 45 degrees, and it doesn't matter which one you pick, because notice what's the same. Opposite is 1, opposite is 1 because they're equivalent angles. So they're going to have equivalent lengths opposite of them. So I can just pick this one right here. Opposite of 45 was 1. Right there. Hypotenuse was square root of 2. And then you go through and rationalize. Square root of 2 on top and bottom. Square root of 2 over square root of 4 is 2. So sine of 45 degrees is square root of 2 over 2. Now, cosine of 45 degrees. Cosine is adjacent over hypotenuse, so that's again 1. Notice adjacent 45 is 1. And the hypotenuse is still square root of 2. We go through and rationalize again. Square root of 2 over square root of 4 is 2. So notice the real interesting on this case, sine and cosine are both, 45 degrees are both square root of 2 over 2. And it goes back to because the adjacent and opposite for both of them are 1. And then cotangent of 45 degrees. So we remember cotangent is reciprocal of tangent. Tangent was opposite over adjacent. So cotangent is adjacent over opposite. So adjacent of 45 degrees is 1. Opposite of 45 degrees is 1. So cotangent of 45 degrees is 1. So we can see that if I've got 30, 60, or 45 degrees, I don't need to be given the triangle because I know the triangle. Where that last section with that 3, 4, 5, I didn't know the angles. I think the angle comes out to be, I couldn't tell you, it's somewhere around 42 degrees or something, I don't know. But whatever the angle happens to be for that 3, 4, 5 triangle, I don't know that angle is associated with 3, 4, 5. But I know 30, 60, 90 is associated with 1 square root of 3 and 2. I know 45, 45, 90 is associated with 1, 1 square root of 2. So if you see these angles, you automatically need to remember these special, these ratios of sides are associated with them. All right, guys, we just worked a moment ago with calculating or evaluating sine, cosine, tangent of 30, 60, and 45 degree angles. Those are the easy to work ones. If we have something that's a little bit more complex, say a sine of 37 degrees, that's one that we can't do by hand because we don't know the ratio of those sides. We'd have to be given the triangle. So if we're given just say sine of 37 degrees, we're going to go to the calculator to evaluate that. Now, first thing you need to make sure you do before you type in sine of 37 and hit enter, you need to go check your mode on your calculator and make sure it's set on degrees because it's sine of 37 degrees that we've been given, not radian. And we'll talk a little bit later what radian means. So we're working in degrees right now, so we're going to go mode to degrees. and then quit. Then we can type in sine of 37 and hit enter. It's automatically understood to be degrees. And so we get 0.601815032. Now, notice I can't math fraction that. Most of the time they won't, because think about what it is. It's a ratio of sides. Sine is opposite over hypotenuse. And most of your hypotenuse are going to have a square root for that. They're going to be irrational numbers. So that's why you can't get a fraction, a rational number from it. So if you'll just put the first 3 decimal places rounded off, 0.602, and that'll be adequate for sine of 37 degrees. Now let's go work another one. Say we have tangent of 15 degrees. So I would hit tangent 15. Our mode is already on degrees, so I go ahead and click enter. Tangent of 15 degrees, 0.268. 9 rounds that 7 up to an 8. So 0.268 would be tangent of 15 degrees. We'll work later on about how to find something like tangent of 15 degrees without using the calculator. It'll come back to the 45 degrees minus 30 degrees, or even 30 degrees divided by 2. Finally, secant. Let's say we have secant of 84 degrees. Now, secant, there's not a secant button, notice, on your calculator. Sine, cosine, tangent. We have the sine to the -1, cosine -1, tangent -1, but those aren't necessarily reciprocal. They don't mean multiplicative inverse like a -1 exponent means. Those mean inverse of sine, inverse of cosine, inverse of tangent. We're going to get to that in a minute. But those are not the same thing as reciprocals. So just remember what reciprocal means. Think of the reciprocal of 2. The reciprocal of 2 is 2 over 1, which is 1/2. The reciprocal of 5 over 1, is going to be 1/5. So if secant is the reciprocal of cosine, cosine is cosine over 1, so the reciprocal is going to be 1 over cosine of whatever the angle is. We said 84 degrees. So secant of 84 degrees is the same thing as 1 over cosine of 84 degrees. So we evaluate that, and it comes out to be 9.567. So that's how we can use the calculator to evaluate all these. And we could do it with the sine of 30 degrees, whatever we did, cosecant of 60 degrees and all that stuff. We can do those on the calculator, but since they're so easy to calculate, we prefer to do them by hand, so we have those exact non-decimal approximation solutions. So now let's use those ideas of calculating with the calculator, those abstract, those not nice to work with angles, and solve some other pieces to triangles. Now, if we look here at example 4, identify the length of the missing side. Notice we're missing the side opposite of the angle we're given. So we're going to use one of our trig ratios that uses the opposite as part of the ratio. Now, look at the other piece you're given. We are, blue marker, we are given the opposite length. We are also given this 3. 3 in this case would be adjacent because it's adjacent to the angle that we're given, the 25 degrees. So we're given opposite and adjacent, so that's 2 trig ratios that use both of those, either your tangent, which is opposite over adjacent, or cotangent, adjacent over opposite. I always prefer to work in those first 3 trig ratios, sine, cosine, tangent, if I can, because we have calculator buttons to help with those. So there's a less converting there. So let's say tangent of our angle, 25 degrees, is equal to opposite over adjacent, or that's just regular tangent definition. Tangent of theta is opposite over adjacent. Now if we tie it back to our triangle, theta in this case is 25 degrees. Opposite of theta was x. Adjacent of theta was 3. Now if I want to know what x is, I've got to get rid of the 3. I've got to solve this equation out. So if it's x divided by 3, how do we move divided by 3? We multiply by 3. So times 3 on both sides. So what I end up with is x equals 3 tangent of 25 degrees. Whatever that happens to be. We can go over to the calculator, punch that in. Type in 3 tangent 25 degrees, and that should tell me what x is equal to, which is going to be 1.399. Which should make, pretty good sense right there, because if this is 3, if this is 25, then that's going to have to be what? 65 degrees? 65 to 3 and 25 to about 1.4 is probably a pretty good ratio of those two sides there, relating back to those angles. So we have found that missing link by using the trig ratio that puts together the information we're given. Well, if we look at number 2 here, look at what's given. I'm given an angle, I'm given the side opposite, and I want the hypotenuse. Well, what uses the side opposite and the hypotenuse? That'd be sine. Sine of theta is equal to opposite over hypotenuse. So sine of, in this case, 75 degrees is equal to the opposite length, 15, over the hypotenuse, x, what we're looking for. I could have done reciprocal in this case so I could have that x on top. It's not going to make that big a difference in the end. And now we just solve. Now be very careful when you're working this one out. I want to move, you realistically want to get x by itself, but x is in the denominator. So I could multiply by x, that moves it over here, and then divide by sine of 75 to get it by itself. But most of the time when y'all see a denominator or a variable in the denominator, y'all usually cross multiply and divide. So that's really what we're going to be doing. We're doing the same thing. Cross multiply x sine of 75 degrees equals 15, and then divide by the sine of 75 degrees. And then I can punch that into the calculator. So if I key into the calculator 15 divided by sine of 75 degrees, I'm going to get x to be 15.529. So x is 15.529. And we see that that probably makes pretty good sense there. Oh, because this is going to be 15. So this is going to be a very, very small side. So these sides are going to be very close, because 75 and 90 are very close to each other as far as size. So the sides opposite should be very close to each other. So that's why 15 and 15.529 are so close to each other. Now let's use that same idea and move over into identifying the angle. Here we took the angle and the sides and used the ratio we were given to solve for the angle. Now let's take the angle and the sides and use the ratio that's given to solve back for the angle. So solve for the side here, go solve for the angle here. Now look at what you're given. We want angle theta, we're given the side adjacent, and we're given the side of, or the length of the hypotenuse. So what uses adjacent and hypotenuse? Cosine. Cosine of theta is adjacent over hypotenuse. So cosine of theta is equal to the adjacent length, 3, over the hypotenuse, which is 5. Now, we want to get theta by itself. Just like before over here, I wanted to get my variable by itself. I multiplied by the 3 because it was being divided. Or on this problem, we cross-multiplied to get the variable by itself. I want to use that same idea of using an inverse operation. I want to move cosine. Now remember, cosine is not a number. It's not a number times theta. Cosine is the operation on theta. So just like when we do logarithms, just like when we do exponents, any of that type of stuff, we move those by doing the inverse operation. So I don't get rid of cosine by dividing by cosine, because cosine is not a number to divide by. I get rid of cosine by doing the inverse of cosine. So I'm going to inverse cosine both sides of this equation. And that's where that cosine to the -1 button on the calculator comes from. So it just goes back to this idea of cosine says what is the ratio of these two sides. Inverse says what angle has a ratio of these two sides. It just asks the opposite question. So all we're going to do here, just like dividing by 3 and multiplying by 3 cancels, cosine and inverse of cosine are going to cancel. Going to leave me theta. On this side, inverse cosine of 3/5, what angle has an adjacent 3 and a hypotenuse of 5? So we just go to the calculator. We're going to use that inverse cosine button. So if I'm going to evaluate inverse cosine of 3/5, I'm going to hit that second cosine button. There's my inverse cosine of 3/5. Just punch it into the calculator, and it's going to spit out the angle. Cosine gives me a ratio of sides. Inverse cosine gives me the angle. So this angle is 53.13 degrees. Now, looking at number 2 here, we got to look at what information is given. I'm given an angle. I'm given the side opposite. I'm given the side adjacent. So what uses opposite and adjacent? Tangent. Tangent of theta is equal to opposite over adjacent. So tangent of the angle we're looking for, theta in this case, is 2 over 4. And you can reduce that to 1/2 if you want to. We're going to punch it in the calculator, so it doesn't matter. It'll do it for you. And then we want to move that theta. Okay? When we wanted to move cosine, we did inverse cosine. When I want to move theta, when I want to move tangent, I'm going to do inverse tangent. Inverse tangent and tangent cancel, leaves me just theta. Inverse tangent of 1/2. And we're going to go to the calculator to do that calculation. So we want inverse tangent of 1/2, second tangent of 1/2, or if you want to leave it to 2/4, that's okay. We get 26.565 degrees. I'm okay with if you round those degrees to the hundredths place to 2 decimal places instead of taking them 3. The trig ratios I like to be to 3 decimal places, but the angles, that's kind of your final answer type thing. So I'm okay if you go to 1 or 2 decimal places on those. If you were going to use that angle for further calculations, it would be better to leave as many decimal points or as many decimal places as possible. Because the sooner you round off, or the more you round off, the more rounded off your final answer will be. But since that's our final answer in this case, I'm okay with 26.57 degrees. So we see that angle theta by using the calculator, inverse tangent of 1/2, angle theta was 26.57 degrees. 26.57 degrees. So that's how we can use those trig ratios, use that calculator and our trig ratios to find different pieces of right triangles. Oh, I should have specified that that was my right angle. Different pieces to right triangles. That's kind of our biggest use. That's what you've used your right triangle trig for the most part up to this point. Just playing around with the different pieces, the angles as they relate back to the sides. Last thing we'll look at in this section is kind of an application of all the little pieces that we've done. Let's look at this problem. Bill wants to build a bridge across a stream on his property, but he doesn't know how wide the stream is, so he doesn't know how long to make the bridge. If he marks a line on one bank as 15 yards long and stands on the other side perpendicular to one end of that line, he must turn 50 degrees to see the other end of the line. How wide is the stream? So there's a lot of information in there. Let's draw a picture. It always helps to draw a picture. So let's draw the stream. Here's the stream. There's the stream. Now, what does it say he does? He marks a line on one bank. So here he is on one bank, marks a line, 15 yards long. And then he stands on the other side perpendicular to one end. So now he's standing on one end of the other side, and he's going to be perpendicular. Perpendicular. So he's got some kind of surveying equipment to be able to calculate all this. Perpendicular to one end of the line. Tells us that from here, here's Bill, there's Bill, he has to turn 50 degrees to see the other end. So he's perpendicular here, but he's got to rotate 50 degrees to see the other end. 50 degrees to see the other end. Now it wants to know what? It wants to know how wide is the string. So it's really just one of those solve for the missing side triangles problems that we worked a few minutes ago. So here's our triangle. Let's identify what we've got. We've got an angle, we've got the side opposite, and we want the adjacent side. So what uses opposite and adjacent? Tangent does. Tangent of theta is equal to opposite length over adjacent length. So tangent of 50 degrees, because that was his angle of rotation there, is going to be opposite 15 over adjacent x. And we just go back into solving the way we did in the last set of examples, or two sets of examples ago. This x is in the denominator, so again we've got to cross multiply. So I get 15 equals x tangent of 50 degrees. Then I divide tangent of 50 degrees. So I'm going to get x equals whatever 15 over tangent of 50 degrees is. So our length, our width of our string, wherever he's going to build this bridge, or how long he's going to build this bridge, has got to be at least this long, whatever 15 over tangent of 50 degrees is. Well, how do we get 15 over tangent of 50 degrees? We go to the calculator, because remember that's not one of our neat 30, 60, or 45 degree angles. So as I can see, I want 15 over tangent of 50 degrees. So I'm going to type 15. I'm going to divide that by tangent of 50. Remember our calculator is already set to calculate in degrees. Hit enter. And we get 12.586. 12.586 what? And what does that mean? Well, let's turn it back into the problem. And the problem was wanting to know how wide Bill needs to make his bridge. So how wide does Bill's bridge need to be? It needs to be 12.59 yards long. Okay, so that's a little bit over almost 39, what, about 38 feet wide long? That's a big wide stream, isn't it? So it's about 38 feet long. He needs to make that minimal, needs to make that bridge there. So that's all the different ways we can use this basic right triangle trig. Just going back through what we've worked on all the way up through from Algebra 1 through Algebra 2 as far as right triangle trig is concerned. Okay, I'll see you in class tomorrow.